Welcome to the mission.
Welcome, fellow explorers, to the frontier of robotic manipulation. This is Munim ul Haq and Syed Amar Ali Jafri, and we are presenting our robotic exploration on vision. Picture this: a world where machines see, interpret, and act, all guided by the marvels of vision. Today, we embark on a journey where theory meets practice, where the intricacies of robot control merge with the art of perception. Vision play an important role in robotic manipulation. Through this vision, we are also able to control our 4-hour robot in lab. After we have found the transformation matrix of manipulators and effector with respect to base frame, since we have to pick up colored object, so in order to find the coordinates with respect to world frame, we have to find transformation matrix of the camera so that we can find the coordinates of the block with respect to base frame. So in this robotic exploration task, we have explored the role of vision in terms of geometric formation of the image to further build on the understanding of control of robotic manipulator. Following are the topics which we will be exploring. Here on the right, we have a three-dimensional depiction of a house. On the left, we have what we will refer to as an image plane, essentially a screen. Now the question at hand is whether an image of the house forms on this screen. When you consider any point on the screen, it receives light from various points on the house. However, what you see isn't a distinct image, rather it's blurred. So one might argue that there is indeed an image forming, albeit a murky one. The real question then becomes, how can we produce a sharp and clear image of the house on the screen? The simplest method to achieve this is by utilizing a pinhole.
Let's first find out what a pinhole is and what is its phenomena. The principle of projection has deep historical roots. Consider the human eye. Light passes through its lens and aperture, eventually being captured by photoreceptors on the retina, as mentioned in the slide. Similarly, in the earliest form of camera, the camera obscura, the second image, light enters through a small aperture in a darkened room, resulting in an image being projected on the opposite wall. This foundational concept persisted and evolved over time, eventually leading to the invention of the photographic camera as we know it today. So here is an example of the camera obscura, where an entirely dark room is illuminated by the light that is passing through this tiny little hole and creating an image of the object outside of the scene, out, outside upside down in this very dark room, of course. Because the aperture is very small and there is no light coming into the room, you have to adapt to the darkness of that room. If you are standing inside that room to actually perceive something, it's actually just very little light, it's not very bright if you create a camera obscura at home. But this has been used. You can find this in various museums that this has been used by artists. Here are some examples which have been mentioned in the slide. You can view these. And on this website below, you can find more examples where ordinary rooms have been illuminated using this principle of a very small pinhole. And then an image has been captured inside that room with a very long shutter time and giving rise to installations like you can see here by the artist. So the most basic physical pinhole camera can be described as a box that has a little hole inside one of the walls. And that hole is collecting light or is letting a light pass through. But it's letting light pass through only into the direction, continuing where the light is coming. So we have a point here then that the light passes through the hole, and because light travels linearly along rays, that light is hitting this image plane, the sensor here or on the back exactly at one location. Because of this, the image that is projected is actually projected upside down onto the image plane behind this little hole of the pinhole in the wall, which is called the focal point, because all the light rays that pass through this hole must exactly pass through this focal point. However, when we consider camera models in this lecture, we typically consider the image plane to be in front of the focal point and not behind the focal point. So here's an example I have mentioned in the slides of being, despite this being the physical model, the mathematical model look like this here on the right side of the slide. The distance from the focal point of this plane is the same as the distance from this image plane to the focal point, but in this case the image plane is in front of the focal point. Now in this case, the image of the 3D object here is of the same size and the same shape as the image if it's projected behind the focal point. The only difference is that it's mirrored, and so both models are actually equivalent, right? They are just related by this mirroring, so they can be brought into each other using appropriate change of image coordinates. Now, further in this lecture, we are considering this mathematical camera model, which has some advantages, of course, in the sense that the image is not projected upside down. So we can directly see the images as we would see it as humans, and that's how digital cameras actually work and store images. They don't store images upside down, but they store them in the right orientation. So this is what we can use as a replacement for this model, because both are equivalent up to very simple reflection. Now if we talk about projection models, there's two basic projection models that we have discovered in our exploration, but these two are the most important as considered by us, but there are many more. But these we will be discussing one here with a slight overview of the other basic projection model. The first model, for which I will only provide an overview here, is the so-called orthographic projection model, where light is assumed to travel parallel to each other rays onto and then projected in that parallel fashion onto that image plane. And in the perspective projection model, the one which we will be discussing further in detail, which is the pinhole camera model, where I have a focal point and all the light rays that passed from a 3D point to the focal point, all the light rays must pass through the focal point, are hitting the image plane at the intersection of that line with the image plane. You can see in the slide that here in this case the size of the object changes, while here the size remains the same. The object has the same size, 3D size, as the dimensions on the image plane, and both of these projection models are relevant. The traditional projection model is really the perspective projection model that is implemented, or that can be approximate almost all the cameras that we know, like our smartphones or digital cameras or DSLRs. But if we use a very large focal length, if you have a telephoto lens, then this perspective projection model can well be approximated by an orthographic projection model. This perspective effects vanish if we use a telephoto lens, and in some cases that actually wanted, for instance, an application where we want to use optics for measurements. Here on the left you can see a so-called telecentric lens that models exactly the orthographic projection process. Because if you model that process exactly and you can measure distances, then afterwards, after projection on the image plane, you know that these distances correspond one to the distances in the real world. So this is used for inspection purposes generally. For instance, here is a comparison between perspective and orthographic projection. On the left you can see perspective, and on the right you can see orthographic projection, and what they do to the image that is formed, and there is a continuous transition in between these two. So here on the left we have a classic, this is all the same cube, but here it's projected using a perspective projection, where the vanishing point is in the vicinity and not an infinity. And we can see that these edges of the 3D cube that are all parallel to each other in 3D are intersecting at this vanishing point that we see here on this image. Now if we increase the focal length, we came to a weak perspective setting, or closer to a weak perspective setting, where this vanishing point moves outside this image domain. And we are considering here that if we increase the focal length even further, if we move the camera infinitely far away from the object, and at the same time increasing the focal length to infinity, which is of course is physically impossible, right? So without such as a telecentric lens, then we can obtain an orthographic projection here, where then all the lines that are parallel in 3D are actually also parallel in the image that is projected in the image that we have captured with the camera. And here on the bottom you can see two examples of perspective projection and orthographic projection, or closer to orthographic projection of a real scene.
A pinhole is an opaque sheet with a tiny hole in it. Additionally, as seen below, it is positioned between the scene and the image plane. Now if you examine a single point on the house, you will notice that a single ray originates at the point P0 in this example, travels to the picture plane, where it projects onto the point Pi. Thus, all of the scene's points now project onto a single spot in the picture. Thus, our goal is to comprehend how P0 and Pi are related to one another. In order to do that, we will first build a three-dimensional coordinate frame called XYZ, which will be positioned at the pinhole with the z-axis, pointing in the direction of the optical axis. By the way, the axis that is marked here and perpendicular to the image plane is the optical axis. Thus, the z-axis is on the optical axis and points in the direction of the image plane. Additionally, the effective focal length, or f, we call here f, is the distance measured between the pinhole and the image plane. Thus, we can now use the vector r0 to write the point using p0. Its coordinates are x0, y0, and z0. Moreover, its image represented by the symbol ri has coordinates on the image plane of xi, yi, and f for the z coordinate. Therefore, the z component on the picture plane will always be f, the effective focal length, regardless of where the point resides in a three-dimensional scene or its z component. Thus, these two triangles right here, the one I am displaying and the triangle that's here on the back behind the pinhole, are comparable to each other. And from these similar triangles, you can write Ri, the vector Ri divided by f, is equal to the vector R0 divided by the Z0. Z0 is, by the way, the Z component of the three-dimensional point, the point in 3D. In other words, it's the depth of the point in 3D. As you can see in the slides, Ri and R0 are vectors. We can break it down into their x component and y component. Say xi by f is equal to x0 by z0, and yi by f is equal to y0 by z0. These are the equations of perspective projection. Very simple equations, but create some fairly non-intuitive effects in images. Now I want to talk about what is the perspective projection of a line in 3D, an essential concept in vision. So here you can see a line in 3D and you have your pinhole right here. And we know that the line and the pinhole, that is a line and a point, define a plane in 3D. And all the rays of light that pass through the pinhole lie on this plane. And for that matter, all the rays of light that pass through the pinhole towards the image plane also should lie on this plane. And so the image of this 3D line on your 2D image must be the intersection, must lie at the intersection of this plane and the image plane. So right here. So in other words, the image of a line in 3D has to be a line in 2D. And this is why you find that in photographs, straight lines in this scene will map to a straight lines in photographs.
We can also formulate this mathematically in terms of a matrix multiplication. If we use a homogeneous coordinates, so as we have seen in perspective projection, 3D points and camera coordinates are mapped to the image plane by dividing them by their z component and multiplying with the focal length. That's what we have just derived. And this expression here in for both the x and y coordinate in regular inhomogeneous coordinates. Now, while this is a non-linear expression because we have to divide by z in homogeneous coordinates, we can write this as a linear equation. So let's assume a matrix called a camera matrix or a projection matrix. There's a 3 by 4 matrix here with the focal length on the diagonal and zeros in the last column. And if we multiply this with the homogeneous 4-dimensional augmented vectors axis of the 3D point, then we will obtain, well, f times xc and f times yc, and then the third coordinate zc. And if we now note, this is a homogeneous 3-dimensional homogeneous vector, and if we normalize that homogeneous vector into an augmented vector where the last element is 1, we obtain exactly f times xc over zc and f times yc over zc in the first two chord elements of this vector, right? So by using this homogeneous representation, we have these points and that are all equivalent to each other. And by the definition of conversion from homogeneous coordinates to inhomogeneous coordinates, we are representing the projection process so that we can express this entire process here with simple linear multiplication. If we assume homogeneous coordinates and then afterwards do the conversion to inhomogeneous coordinates by dividing by the third element of the homogeneous vector. So the important point here is the projection is linear when using homogeneous coordinates. And after the projection, again as in the orthographic case, it's impossible to recover the distance of the 3D point from the image. As little remark, the unit for f is typically chosen as pixels to convert metric 3D points into pixels. If you look at this expression here on the slide, we have a 3D point that expressed in meters. So we have a x and z being defined as meters, but the scene coordinates are supposed to be in pixels, and of course the unit of f has to be also defined in pixels because the meters cancels here, and so the only thing that remains is the screen coordinated pixel, and that's why the focal length in our models that we are using is often going to be defined in pixels. This is the most basic form of the pinhole projection principle, but we can add further more parameters, and one important parameter is a so-called principal point. But why do we need a principal point? Well, in the previous model that I have explained to, the image coordinate system, and this is now a 3D illustration of this one here. The image coordinate system is defined on the principal axis. It's centered on the principal axis, but it's inconvenient to store pixels with negative coordinates. Consider a pixel here that would have negative coordinate with respect to that coordinate system. So what is done in practice is, and also I have already, as you can see, the oriented the as you can see here, the oriented the coordinate system in a way that is convenient to store images. What we can do here is we can move the coordinate system to the top left of the image. So this is the viewpoint here. So looking from behind, this is the top left corner of the image, and so the first pixel here, well, if we move this coordinate system, will be located at 0 or 1. If you use a 1 based coordinate system, which is much more convenient to store image arrays, and that's what we typically do in practice. We don't consider negative pixels, but we consider just positive pixels and define the image coordinate system here, which means that this principal point here must be added to the image coordinates such that we obtain only positive coordinates, and that's called the principal point xc and yc, and that's added to the pixel coordinates after this projection that we was discussed in the previous slide. So the complete perspective projection model without distortion is given by this equation here, where you can see that now in addition to this multiplying the focal length with x divided by c, we also now have a translation by the principal point, and we have done two more modifications here. One modification is that we have allowed the focal length in x direction to differ from the focal length in y direction, and we have added another scaling factor here that allow for this. This is called the skew, that allows for modeling sensors that are not mounted perpendicular to the optical axis due to the manufacturing inaccuracies. Fx and Fy, however, would only be independent from each other if we have different pixel aspect ratios, and sensors are manufactured typically pretty precise. So in practice, what we often do is we set Fx equal to Fy, and also this skew is typically very small. So in practice, often the skew is considered 0. But we have to model in almost all cases that we consider the principal point, right? So while f can be set the same and s can be set to 0, the principal point is still an important parameter that we want to estimate in the world on a model now. This is the full camera matrix that is defined through all these parameters, and this is called the intrinsic matrix because it's, and actually this is the projection matrix, the 3x4 matrix, but the 3x3 submatrix here in front is called the calibration matrix K, here denoted in red. And this is called the intrinsic matrix because it stores all the intrinsic parameters of the camera, everything that's intrinsic to the camera, like the focal length, the sensor ratio or the pixel ratio, the principal point, and so on. This is opposed to the so-called extrinsic parameters, which is the camera pose with respect to some world coordinate system. That's why it's called intrinsic parameter. And the projection then can be done in homogeneous coordinates by just taking this 4-dimensional homogeneous vector, so representing a 3D point in camera coordinate system, and projecting it by multiplying it with this matrix.
One thing that's nice about this homogeneous representation is that we can change transformations. So if a 3D point is not represented in camera coordinate system but is represented in world coordinate system, we can change the transformation, the rigid body transformation that maps a point by multiplying it with this rotation and translation matrix. This is an Euclidean transformation under we have seen before, so it multiplies that point and afterward multiplies that point that is now in camera coordinates with this with the intrinsic matrix. So we have the extrinsic and the intrinsic matrix here onto the image plane. We can also do this by simply multiplying these two transformations together into one matrix, and now we have just to do one matrix multiplication instead of two matrix multiplications. and in many cases that's very convenient and can also save time and be more efficient. So here's the mathematical formulation of this. So we have the screen coordinate, which is equal to the camera coordinate or the camera 3D point in camera coordinates, multiplied with the intrinsics, which is equal to the point in world coordinate multiplied with the extrinsics and the intrinsics, and then we can multiply these two matrices together. This is a 3 by 3 matrix, and this is a 3 by 4 to obtain 3 by 4 projection matrix that directly maps a point from world coordinate to the screen. And this 3 by 4 projection matrix P can be pre-computed, can be pre-multiplied and then applied for all the points where we want to apply this projection on. Sometimes it's preferable to use a full rank 4 by 4 projection matrix, where instead of 3 by 4 matrix with the intrinsics and a 4 by 4 matrix for the extrinsics, we have also a 4 by 4 matrix for the intrinsics, where we simply have added the last row with zeros and a 1 in the last element. Now this is, of course, if we multiply these together we get a 4 by 4 matrix, and now we can take this homogeneous vector, this 4D representing a 3D point, and projecting it through this matrix and obtain now a 4-dimensional homogeneous vector x tilde. But because we know this is a point that's on the image screen, we must still normalize this with respect to normalize this vector with respect to the third coordinate, not with respect to the fourth coordinate. And so what we obtained is this expression here, as we have shown in the slide, which is familiar because the first three coordinates are the same. The third coordinate is 1 by definition, and we have this projection here in the first two coordinates, and then the last coordinate here is the inverse depth, as you can see from the slides. And because of this fourth component of this inhomogeneous 4D vector is the inverse depth, if the inverse depth is known, we can use this full rank matrix to also do the inverse. So assume we have this vector where we know the depth, we know the inverse step as well. Then we can also, now because it's a full rank matrix, we can invert it and go from an image point to the 3D point, and afterward in order to extract the 3D point we need to normalize with respect to the fourth entry, because now we have a point in 3D space, but of course we need to know the depth, otherwise this wouldn't be possible. Good.
So using this we get a matrix known as a camera matrix or projection matrix, as I've already referred. So it will be used to find the coordinates of any object placed into the base frame or the world frame. Like in our course and the lab of Introduction to Robotics, in order to find the joint angles using inverse kinematics, we must have XYZ coordinates of the object in the reachable workspace. The camera is used to obtain the coordinates in the camera frame. The coordinates obtained through camera is multiplied with the camera matrix or the projection matrix to get the coordinates of the object in the world frame. Using this we can effectively perform the task of specifically pick and place of any object using the robot, specifically what we have done in our lab 8 of the course.
Since we are time constrained, but we got interested in the topic of vision, so we explored the idea of exposure time as well, whose brief overview is provided as follows. So here's an image of Flatiron building in New York, and one of the interesting things you can notice is that image is pretty much focused everywhere. So pinhole camera, well designed pinhole camera, tend to create these sort of all focused everywhere images. It's a very nice image. It used effective focal length of 73 millimeters, a pinhole of diameter 0.2 millimeters. But here's the price we pay: the exposure time. It's 12 seconds. So since a pinhole captures very little light, it lets very little light through. As a result of that, the exposure times tend to be much longer, so that the detector that you are using to capture the image has enough photons that arrive on it. And so you can imagine that almost for any real application of computer vision, waiting for 12 seconds to capture a single frame is just not going to work, and that's why we use lenses. This is all we have discussed. Thank you for your time, and here are the references.
Welcome to the mission.